Hello everyone, today my group, which is group 13, is going to present linear algebra group assignment. Here are my group members. My group members are Nichian, Liu Huibun, Liu Yiting, Cha Shishen, and me, Stephanie Ng Yijing. A 3 times 3 non-diagonal symmetric matrix that we have chosen is A equal to 3, 2, 0, 2, 6, 0, 0, 0, 4. This matrix is clearly a non-diagonal matrix because there exists non-zero value in diagonal area. And it is symmetric because A transpose is equal to A itself. The first question is to obtain the eigenvalue and eigenvector of A. To obtain eigenvalues of A, we will use characteristic polynomial, which is determinant of A minus lambda I equal to 0. Then we substitute the value into this equation and solve the determinant of A minus lambda I equal to 0. We will use the first row and finally we will get negative lambda power of 3 plus 13 lambda power of 2 minus 50 lambda plus 56. To solve this polynomial, we need to find the roots of polynomial by finding the divisor of 56, which is positive negative 1, positive negative 2, positive negative 4, positive negative 7, positive negative 8, positive negative 14, positive negative 28, and positive negative 56. By testing which divisor value is equal to 0, we find out that 2 is one of the root of polynomial and eigenvector of matrix A. Then we can factorize the polynomial as lambda minus 2 times a quadratic polynomial. To find out the quadratic polynomial, we use long division and get that the quotient is negative lambda power of 2 plus 11 lambda minus 28. Therefore, to solve this quadratic polynomial, we use quadratic formula, which is lambda equal to minus b plus or minus square root b squared minus 4ac divided by 2a. Then we will obtain that the second lambda is equal to 4 and the third lambda is equal to 7. Hence, the eigenvalues of matrix A are lambda 1 equals to 2, lambda 2 equals to 4, and lambda 3 equals to 7. To find eigenvector, we solve the equation which is A minus lambda ix equal to 0 vector for vector x. First, lambda is equal to 2. We substitute the lambda equals to 2 into equation and make it into augmented matrix form and then solve it until it becomes REF form. After that, we obtain that x1 and x3 are leading variable and x2 is free variable. So we let x2 equal to t. From the REF form matrix, we get that x1 plus 2x2 is equal to 0 and x3 is equal to 0. Since we let x2 equal to t, so x1 plus 2t is equal to 0 and x1 is equal to negative 2t. Hence, we get the solution space of x is negative 2t, t, 0. And we factorize t, then we will get t, negative 2, 1, 0. So the eigenvector for lambda equals to 2 is x vector equal to t, negative 2, 1, 0. Next, for eigenvalue lambda equals to 4, we use the same method to solve it, but this time we substitute the lambda is equal to 4. Then change it into augmented matrix form, then solve it until it becomes REF form. After that, we obtain that S1 and S2 are leading variable and S3 is free variable. So we let S3 equals to S. From IF4 matrix, we will get that S1 minus 2 X2 is equal to 0 and X2 is equal to 0. Since S2 is equal to 0, we will get that S1 is equal to 0 from the equation S1 equals to 2X2. Hence, we get the solution space of S is 0, 0, S, and we factorize S, we will get S 0, 0, 1. So eigenvector for lambda equals to 4 is S vector equals to S 0, 0, 1. For the last lambda equal to 7, we use the same way to solve, but we substitute the lambda is equal to 7. Then change it into augmented matrix form, then solve it until it becomes IEF form. Hence, we will get that x1 and x3 are leading variable and x2 is a free variable. So we let x2 equal to W. From the IEF form matrix, we get that x1 minus 1 per 2 x2 equal to 0 and x3 is equal to 0. Since we let x2 equal to W, we also obtain x1 is equal to 1 per 2W from the equation x1 minus 1 per 2W equal to 0. Hence, we get the solution space of X is 1 per 2W, W0. And with factorize W, we will get W 1 per 2, 1, 0. So the eigenvector for lambda equal to 7 is X vector equal to W 1 per 2, 1, 0.
Use P that diagonalize A to calculate A power of 21. A square matrix A is called diagonalizable if there is an invertible matrix P such that P inverse A P is a diagonal matrix. Then the matrix P is said to diagonalize A. To form a matrix P, we need to use the linearly independent eigenvector of A, which are P1, P2, and P3 from a previous question. So now we have formed a matrix P, and the next step is to find the P inverse. The formula to find the P inverse is 1 over determinant of P multiplied with adjoint of P. Therefore, we need to find the determinant of P first. And here, we are using cofactor expansion on third row, and we get the determinant of P is 502. After settle determinant, we need to find adjoint, and there are three important steps to find the adjoint. First, we need to find the minor matrix. After that, to find the cofactor, and lastly, the adjoint is a transpose matrix of the cofactor matrix. Now we have all elements to form an inverse matrix, and this is our P inverse matrix. And hence, we can obtain the diagonal matrix and show that matrix A is diagonalizable. In general, we may show that for any positive integer k equals to P inverse A power kp. Since A is diagonalizable and P inverse AP equals D is a diagonal matrix, thus it is easy to compute A power of 21 by using this formula. Question 3. Assume that A is a standard matrix of TA such that TA maps R cubed to R cubed. Obtain TA, kernel TA, and range TA. To obtain the TA, we have to multiply the standard matrix of TA, which is A multiplied by the column vectors of X, which also denoted X1, X2, and X3 in the matrix form. Then we got a 3 by 1 matrix as a result of TA. The first row equals to 3x1 plus 2x2. Second row equals to 2x1 plus 6x2. And the third row equals to 4x3. After that, we need to rewrite them in the form of linear transformation. TA is equal to 3x1 plus 2x2, 2x1 plus 6x2, and 4x3. Next, to find the kernel TA, we know that if T maps V to W is a linear transformation, then the vector in V that T maps into 0W is called the kernel of T, denoted by kernel T, and in this case, the V and W replaced by R cubed. Suppose that the linear transformation of TA equals to 0, First, we can easily get three equations from here, which are 3x1 plus 2x2 equals to 0, 2x1 plus 6x2 equals to 0, and 4x3 equals to 0. Secondly, we use it to form an augmented matrix and we perform the ERO until we get REF matrix form. As you can see here, we get x1, x2, x3 equals to 0, and the solution of the kernel TA is 0, 0, 0, which is equals to 0 R cubed. And the last thing we need to obtain in this question is to find the range of TA. Range TA is a set of all vectors in W and here replaced by R cubed that are image on the TA of at least one vector in V, which is R cubed, also can be denoted as RTA. We need to consider that there are three scalars which are A, B, C, and they are equals to the linear transformation of TA. So let A, B, C as an element of R cubed. There exists x1, x2, x3 such that linear transformation of TA equals to ABC, which is 3x1 plus 2x2, 2x1 plus 6x2, 4x3 equals to ABC. And we can get three equations, 3x1 plus 2x2 equals to A, 2x1 plus 6x2 equals to B, 4x3 equals to C. And in the next step, we need to form an augmented matrix again and perform ERO until it is in REF form. And you can see here, x1 equals to 3a minus b over 7, x2 equals to 3b minus 2a over 14, and x3 equals to c over 4. Therefore, the range of TA is given by ABC is the element of R3.
We proceed to question 4. In question 4, we need to assume that P is the transformation matrix of TP such that TP is a mapping from R cubed to R cubed. Then we need to obtain TP, kernel TP, and range of TP. We obtain TP first by holding activity property and homogeneity property in the matrix transformation theorem. We know that the formula of TPX equal to PX if formed, and every vector X must be in the R cube. Then we substitute the x1, x2, and x3 as vector x and matrix P. Then we obtain in the question before into the formula. By multiplying P with vector x together, we can obtain TP in which TP is negative 2x1 plus 1 over 2x3, x1 plus x3, and x2. Then we need to write the TP in a proper way in which TP equal to negative 2x1 plus 1 over 2x3, x1 plus x3, and x2. Next, we need to find kernel TP. The kernel of TP consists of all x that is element in R cubed and TPX equal to 0. By substituting all the elements of TP in the formula, we create a system of linear equation, which is negative 2x1 plus 1 over 2x3 equal to 0, x1 plus x3 equal to 0, and x2 equal to 0. By using equation 2, we substituting x1 equal to negative x3 into equation 1, then we can obtain x1, x2, and x3 equal to 0. Thus, we can conclude that kernel TP is 0, 0, 0, and we can say that it is a 0 R cube. Lastly, we need to find the range of TP by letting ABC in the element of R cube when there exists of x1, x2, x3 is the element of the R cube such that TP equal to ABC. Then we can substitute the TP into the formula and we create an equation in which negative 2x1 plus 1 over 2x3, x1 plus x3, x2 equal to ABC. Then we need to create a tree system of linear equation again, in which first equation is negative 2x1 plus 1 over 2x3 equal to A, x1 plus x3 equal to B, x2 equal to C. By using equation 2, we can create a x1 equal to negative x3 plus b, and we need to substitute it into the first equation, and we can get the x1 equal to negative 2a plus b over 5, x2 equal to c, and x3 equal to 2a plus 4b over 5. In conclusion, the range of TP is ABC, in which an element of R cubed. We also can set that the range of TP is equal to R cubed. Next, we continue to question 5. In question 5, we need to assume that A is a standard matrix of TA such that TA is mapping from P2 to P2. Then we need to obtain TA, kernel TA, and range of TA. First, by letting vector P to be the element of P2, we can assume that P equal to A0 plus A1x plus A2x squared. Based on the information in the question statement which say that A is a standard matrix of TA, thus we can substitute matrix A into TA. Then we use formula of TAP equal to TAPX that multiply matrix A with A0, A1, and A2 to the basis of 1x and x squared. Finally, we can obtain TAP equal to 3A0 plus 2A1, 2A0 plus 6A1, and 4A2 to the basis of 1x and x2. To write the TAP in proper way, we can say that TAP is equal to 3A0 plus 2A1 plus 2A0 plus 6A1x plus 4A2x squared. Next, we need to find the kernel TA. We know that the kernel TA equal to 0 P2, in which by multiplying basis of P2 with 0, we can obtain 0 plus 0x plus 0x squared. Then, by substituting out of the element of TAP and 0 plus 0x plus 0x squared in the formula, we can create system of linear equation in which 3A0 plus 2A1 equals 0, 2A0 plus 6A1 equals 0, and 4A2 equals 0. By using the system of linear equation, we can create an augmented matrix and doing the ERO until we reduce it into the RREF form, we can see that A0 equals 0, A1 equals 0, and A2 equals 0. To write the kernel TA in a proper way, we can know that kernel TA is 0 plus 0x plus 0x squared equal to 0 P2. Lastly, to find the range of TA, we need to let range of TA equal to B0 plus B1x plus B2x squared as an element of the range of TA, in which there exists of Px equal to A0 plus A1x plus A2x squared as an element of P2. Then we can say that range of a TP is equal to the B0 plus B1x plus B2x squared. By using all of the information given above, we can create an equation in which 3A0 plus 2A1 plus 2A0 plus 6A1x plus 4A2x squared equal to B0 plus B1x plus B2x squared. By using this equation, we can create a system of linear equation and create an augmented matrix. By doing the ERO, we can reduce the augmented matrix into the RREF form to obtain that A0 equal to 3B0 minus B1 over 7, A1 equal to 3B1 minus 2A0 over 14, and A2 equal to B2 over 4. Lastly, as a conclusion, we need to write the range of TA in a proper way. Thus, we can say that range of TA is B0 plus B1x plus B2x squared in the condition of TA equal to B0 plus B1x plus B2x squared. Then we can say that the range of TA is equal to the P2.
For question 6, we need to find P prime that orthogonally diagonalize A using the Gram-Schmidt process on the columns of P from question 2 in space R3 given the Euclidean inner product. For matrix P, we denote column P as element U1, U2, and U3, which U1 equal to -2, 1, 0, U2 equals to 0, 0, 1, U3 equals to 1 over 2, 1, 0. By using Gram-Schmidt process, we denote as V here by using the formula given in Gram-Schmidt process.
First step, it said that V1 is equal to U1. Next, we find V2 by using the formula U2 minus the inner product for U2 V1 divided by the square of norm V1 and multiply with V1 that we get from the previous step, which is the vector -2, 1, 0. Then we got the answer for V2, which is 0, 0, 1. Next, we find the V3 using formula in Gram-Schmidt process, which U3 minus inner product of U3 V1 divided the square of norm V1 and multiply it with V1, then minus the inner product of U3 V2 divided the square of norm V2 multiply with V2 that we get from the previous step, which is 0, 0, 1. Then we get the final answer of V3, which is 1/2, 1, 0. Now we get the answer for V1, V2, and V3, and we rewrite it in the form of orthogonal basis. V1 equals to -2, 1, 0, V2 equals to 0, 0, 1, V3 equals to 1/2, 1, 0. We can check whether the new element V1, V2, V3 are orthogonal or not. We identify for the inner product for V1, V2, V2, V3, and V1, V3. We observe that all the inner product is 0. Thus, the new element V1, V2, and V3 are orthogonal set in the Euclidean inner product. Next, in order to form an orthonormal set from an orthogonal set, we need to normalize the set. We notice that for norm of element, V1 and V3 are not equals to 1, so they are not an unit vector. Thus, we sub into the formula where we multiply 1 over the answer of each norm into each of the element of V1, V2, and V3. We observe that the norm of V2 is equal to 1, thus we still will get same vector V2 in final, which is 0, 0, 1. We got the three sets of orthonormal bases. Lastly, we rewrite them in the form of orthonormal bases that's shown in the slide. Finally, we get P prime from orthonormal set, which equals to -2 sub 5/5, sub 5/5, 0, 0, 0, 1, sub 5/5, 2 sub 5/5, 0.
Now, I'm going to explain further about the last question. This question asks us to show that P prime from question 6 is orthogonally diagonalize A given the Euclidean inner products. We also need to find out that whether the P prime is also orthogonally diagonalize A given the weighted Euclidean inner products. For step 1, we need to show that P prime is orthogonal. We use the knowledge that we learned from topic 4.3, which is when a square matrix A with property A inverse equals A transpose, it is said to be orthogonal matrix. Thus, a square matrix A is orthogonal when A times A inverse or A transpose times A is equal to identity. So, we substitute the P prime transpose and P prime that obtained from question 6 into this formula. Then calculate and get the identity matrix. Hence, we have shown that P prime is orthogonal. Secondly, we need to prove that P prime from question 6 is orthogonally diagonalize A given the Euclidean inner products. Again, as what we learned from topic 4.3, n times n matrix A is said to orthogonally diagonalizable if there exists an orthogonal matrix P
such that P inverse times A times P equals to P transpose times A times P, and both of them are equal to D, is diagonal. Then the matrix P is said to orthogonally diagonalize A. So now we substitute the P prime transpose A and P prime into the equation and calculate. We get the matrix 2, 0, 0, 0, 4, 0, 0, 0, 7, which is the same as the diagonal matrix that get from our question 2. Therefore, we can make a conclusion that since P prime transpose times A times P prime equal to D, we show that P prime is orthogonally diagonalize A given the Euclidean inner products. Now, we come to the step 3. We need to use the Gram-Schmidt process again to find the new orthogonal basis as the question given the weighted Euclidean inner product. We use back the column from matrix P, which we denoted as element U1, U2, and U3. First, it is said that V1 equals to U1 and equals to negative 2, 1, 0. While for step 2, we need to use this formula, which is U2 minus inner product for V2, V1 divided by the norm of V1 square and multiply with V1. Now, we're focusing on the inner product for V2, V1 and norm for V1. The formula have shift according to the weighted Euclidean inner product that has been given in the question. So, to make sure we use the weighted Euclidean inner product that has been given. Thus, we get the answer for V2, which is 0, 0, 1. Next, we find the element for V3, also by using the formula in Gram-Schmidt process, which is U3 minus inner product for U3 V1 divided by the norm of V1 square and multiply with V1 minus inner product for U3 V2 divided by the norm of V2 square and multiply with V2. And again, don't forget for the inner product for U3 V1 and U3 V2 and also the norm used formula for weighted Euclidean inner product that has been given. Then we will get the answer for V3, which is 5 over 6, 5 over 6, 0. So now we have done calculating all V1, V2 and V3. Then we can write the orthogonal basis as shown at the slide. Then we're moving on to the orthonormal. We need to check whether orthogonal basis V1, V2 and V3, our unit vector has norm 1 as we learned from topic 6.3. So, we equate each of the value of the element into the right weighted Euclidean inner product norm formula, and we found out that 3 of them is not unique vector since them are not equal to 1. Therefore, all we need to do is use the element of V1 that we get just now to divide the answer of the norm of V1, and we got the answer Q1 as one of the set of the orthonormal. Same goes to the element Q2 and Q3. Thus, we can write the orthonormal basis as shown below. Lastly, we can write back the P prime from orthonormal basis to check whether our P prime is orthogonal matrix or not. Once again, we use the knowledge we learned, which is P prime transpose times P prime. Since we didn't get the identity matrix, this showed that P prime is not an orthogonal matrix. Here comes our last step of question 7. We need to find out whether P prime transpose times A times P prime equal to 0 by using the knowledge of topic 4.3 that we already used in the step 2. We find the transpose of P prime and substitute the P prime transpose A and P prime into the equation and calculate. We get the matrix 5 over 3, 0, negative third 2 over 3, 0, 4 over 3, 0, negative third 2 over 3, 0, 13 over 3, which is not a diagonal matrix. Since P prime is not an orthogonal matrix, and P prime transpose times A times P prime is not equal to D, we conclude that P prime doesn't orthogonally diagonalize A given the weighted Euclidean inner products. That's the end for our group discussion, and that's all from us. Thank you.